Daisy is a photographer and she is given a top view photograph of a table containing different objects on it, representing a 2D plane. Now she wants to capture the objects from the side view, that is, the objects need to be projected on a 1D vector without losing much of the context within the objects. Since she is a professional photographer, she tries to capture the objects from different angles, and she finds out the most optimal angle that keeps the distances between the objects as similar to that of the original image. That is, the projection that loses the minimum information or the context. She also observes that this angle turns out to be the angle that maximizes the spread between the objects. Hello everyone and welcome back to my channel on Think Upon AI. So today we have an interesting topic to discuss, which is principal component analysis in machine learning, also known as PCA. Now, just like Daisy, there are people in the field of machine learning that need to face similar situations. I'll explain that in a minute. In machine learning, there are real-world scenarios where we need to model functions that depend on huge number of input parameters. That is, the function being high-dimensional. This higher dimensionality could affect the performance of a machine learning model due to several other reasons, one of them being the curse of dimensionality. Now, in order to avoid that, one of the approach is to project these high dimensional data to lower dimensions, just like the task of Daisy. In machine learning, PCA is one of the techniques that help us to do so. Okay, so now we know why do we need PCA. But the next immediate question that comes into our mind is, what exactly is PCA? So this is the whole outline for today's video, where to begin with, we would be discussing about feature extraction and feature selection in the context of dimensionality reduction. Then I would try to give you an intuition about the eigenvectors and eigenvalues in matrices. If you already know about these topics, you can directly jump onto the next section, but it never harms to revisit the important concepts. In the next section, we would be discussing about the steps that are involved in order to calculate the principal axis or principal components in PCA. At the end, I would also like to give you a simple example that will help you reinforce the discussed steps. Let's jump into it. Let us start with feature selection versus feature extraction. Now imagine you are at a nice and cozy restaurant on a summer evening in Italy. There, while eating, you come across a survey done by one of the restaurants on the feedback of the wines they serve. The quality of the wine was assigned as per the subjective taste of their customers, and it was mapped to particular parameters of wine for their future reference. You notice that the quality of the wine was mapped to two features, one being the amount of the residual sugar in it, and second being the quantity of the wine served to the customer. Now, being a nice data analyst, immediately you observed that the wine quality could not depend much on the quantity of the wine served, and hence is a redundant feature for the survey. In a crude way, you did a feature selection here based on the feature importances. So to define, feature selection is a way of selecting the subset of the most relevant features from the original feature set by removing the redundant, irrelevant, or noisy features. Now, feeling proud about your skills and eating a heavy meal, you start walking towards the next restaurant for a nice dessert. You notice the next restaurant also have a similar survey, but this time they have considered different feature set, that are the residual sugar and the alcohol content in it. This time again you try to reduce the feature space to increase the effectiveness of the survey, but this time you are not able to choose or eliminate one of the features as both of them look equally important to you. In other words, feature selection is not possible in this case. Instead, you have to use feature extraction when new features must be formed using raw feature space. Looking at the graph, you can try making new features that is a combination of the two features along the shown vector. Wonderful, you did feature extraction in this case. So, to define feature extraction, it is a way of transforming raw data into features that are compatible with machine learning models. You will learn more about feature extraction in the later part of this video. Okay, let us start with the next section where we'll try to have an intuition about the eigenvectors and eigenvalues in matrix multiplication. To understand this, we must first understand that any matrix multiplication is a linear transformation in the coordinate space. Let us take an example for this. Let us assume there is a 2 by 2 square matrix A and a vector in a two-dimensional coordinate space with one unit in x direction and one unit in y direction. Now if I multiply this vector with the matrix A, we'll get a new vector which has 3 units in the x direction and 6 units in the y direction. Now if we plot this on a graph, we see that the vector x has been transformed to a new vector y with the help of matrix multiplication through A. Now imagine just like that every vector in the coordinate space is transformed by this matrix. In a way we can say that the whole coordinate space is transformed, which can be seen as stretching or rotating a fabric. All the vectors on this fabric will be transformed accordingly. However, there are some vectors in the coordinate space which when multiplied with the matrix A cannot change their direction. They can only shrink or stretch in the same direction as they are. These vectors are called eigenvectors. And to illustrate this whole concept, we'll take a look at a visualization tool from GeoGebra. Okay, so here is a nice visualization tool provided by GeoGebra, which will help us visualize the linear transformations from the matrix multiplication which we have seen before. On the left hand side, you can see the standard coordinate space which will be multiplied by the matrix A to give us the output coordinate space which will be shown on the right hand side of the screen. Now, since the matrix A is an identity matrix, we can see both the input and output coordinate space are same. But if I change some of the values of my matrix, we can see on the right hand side the coordinate space is linearly transformed through the multiplication by matrix A. Further, if I show you the vectors inside the coordinate spaces, you can clearly see the transformations being done on each of them. So each of the vector is being transformed by changing its direction as well as its magnitude. But there are few vectors on this coordinate space which will not change their direction, also called eigenvectors. I'll show you few of them. So this is one of the eigenvectors since the direction in the input and the output coordinate space are same. And even the magnitude in this case are same. But let's say for this vector, the direction is kept similar. So this is an eigenvector in our case, but the magnitude is doubled. So further, the eigenvalues represents the magnitude by which the eigenvector is being stretched or shrinked. In this case, the eigenvalue for this eigenvector is 2, while the eigenvalue for this particular eigenvector is 1. So from now on, whenever you think about eigenvectors and eigenvalues, always try to imagine eigenvectors as the vectors which don't change their direction through the matrix multiplication which is being done, while eigenvalues are the values by which the magnitude of these eigenvectors will be changed through the matrix multiplication. Now, since we have an idea about the required background, we can finally move on to the next section to understand the steps that are involved to perform PCA on any problem. As we learned from Daisy, the most optimal way to project information to lower dimension is to choose vectors that have maximum variance in the projected data. And through optimization of the mathematical formulation of the above observation, researchers found out that the eigenvectors of the covariance matrix of the dataset are the vectors with maximum variance, also called principal components. Based on the above findings, we first need to find the covariance matrix and then we need to find the eigenvectors of the covariance matrix which will represent the principal components in PCA. So here are the steps for PCA. Step 1. Mean centering. As the name suggests, we'll center the mean of our dataset first such that the dataset is distributed with the mean at the origin of the coordinate space. It will help us better optimize the method. Step 2. We'll find the covariance matrix for our dataset. Step 3. We'll calculate the eigenvectors and the eigenvalues for our covariance matrix. Step 4. Once we have our eigenvectors, which represent the principal components in our method, we'll select the principal components with respect to the eigenvalues and then we'll project the data points along the selected vectors. Let us understand all the steps with an example. If you remember, this is the survey that you came upon while roaming in the beautiful streets of Italy. We discussed how you can do feature extraction in this particular case. Since PCA is also a type of feature extraction technique, we can apply the steps involved to find principal components for this example. Step 1. Mean centering. In this step, we find the mean of the dataset for each of the columns. So, the mean for the residual sugar content is 2.2 while the mean of the alcohol content in wine is 9.65 based on the sample dataset. Next, we subtract the mean values from each of the data entries with respect to each column mean. This will center the data distribution around the origin. Now, it is not a mandatory step, but it is observed that including this step always improves the PCA optimization. Step 2. Calculate the covariance matrix. The covariance matrix generalizes the concept of variance to multidimensional problems. The matrix is a square matrix where the diagonal elements of the matrix are the variance of individual variables, which represents the spread across each of the variable, while the non-diagonal elements are the covariance between the random variables. The covariance measures the relationship between them. Now, in order to calculate these for our example, we need to refer to the equations as to how they are calculated. The variance is calculated by summing the square of the difference between each element value and the respective mean value. It is then divided by the total number of data entries in our sample dataset to get an average. Whereas the covariance is calculated by summing the product of the difference between each element and the respective mean value for each of the random variables. It is then divided by the total number of data entries in our sample dataset. Since we already did mean centering on our data, the mean for both of the variables are 0 in our case. So the equations can be further simplified. Based on this, the covariance matrix is calculated. Step 3. Find the eigenvectors and eigenvalues for our covariance matrix. Now, as we already know about eigenvectors and eigenvalues, we can directly jump on to see how to calculate them mathematically. We have our covariance matrix and we also know about the properties of eigenvectors, that the matrix multiplication with the eigenvector can be written as a scalar multiplication where lambda represents the eigenvalue for that particular eigenvector. Further, we can rearrange the equation to get this form. Now, if a matrix when multiplied with any non-zero vector should give a 0 value in every case, then it must have its determinant to be 0. I'll not dive deep into why is that so, but to give you an idea, in order to fulfill the above condition, it is required that the matrix must be non-invertible and so its determinant needs to be 0. We can put the values in the equation to get our final equation in the quadratic form with respect to lambda. Solving the equation using standard formula, we get lambda 1 equal to 4.67 and lambda 2 equal to 0.13. These values represent the possible eigenvalues with respect to the covariance matrix. Once we have the eigenvalues, we can one by one put the values in equation 1 to get the respective eigenvectors. If we put lambda 1 first, we get a certain ratio between the components of the vector in 2D space. To find the unit vector, we can assume the first component to be equal to 1 and then substitute to get the value of the second component. Then we can divide the vector with the magnitude to get u1. This is the first eigenvector with eigenvalue 4.67. Remember, that means in the transformed space this vector is stretched by the magnitude of 4.67. Similarly, we can find the second eigenvector by substituting the second eigenvalue to get u2. Once we have the eigenvector or the principal components, we can also visualize them on the plot. Looks great. So we have our principal components. Now, since we need to project the 2D feature space to 1D dimension, we need to select one of the two eigenvectors that we have. To do so, the eigenvector with the highest eigenvalue is selected first. This vector also represents the vector with the maximum variance of the projected dataset, which we always wanted. So we can select the principal component 1 and move on to the final step. Step 4. Project the data on the selected eigenvector. Now in order to project your data, we need to simply do a dot product of each data point vector with the principal component that we have selected. This is simply a matrix multiplication when handling vectors. For example, for the first data point, where x1 is equal to 0.9 and 0.7, we can find the projection by matrix multiplication of u1 transpose x1, which gives us the value of 1. This is the value of our first data point when projected on the selected principal component vector. Similarly, we can project all the vectors to get the final data set projected in one-dimension feature space. And finally, we have our new feature column that will help improve the survey at the cafe. Now you can relax and eat your dessert if you forgot to eat it. This was a simple explanation video explaining principal component analysis, aka PCA, in machine learning. If you found it helpful, do give it a thumbs up and hit that subscribe button for more such videos. Also, if you want me to make a video on Python implementation of PCA or on any topic that you want me to explain, do let me know in the comment sections below. Thank you for watching.